The purpose of this really short module is to set up some convenient notation for Taylor polynomials. Let f from AB to R be a CK function. CK function. We define the nth degree Taylor polynomial of f centered at C in AB by I must mention nth degree n less than or equal to k, of course, by T n of f comma c comma x to be by definition equal to summation I equals 0 to n the ith derivative of f at the point C divided by I factorial into x minus c the whole power I. Okay, so you can view this as a polynomial in the variable x. Okay, notice also that t0 of fcx is just f of c. This is a constant. Okay, now we also define the Taylor series, or I should write the infinite Taylor series of f centered at C provided f is infinitely differentiable at C. You will see more about such functions which are known as smooth functions in the next module. Okay, so this just means that you can repeatedly take derivatives of f at C. F prime of C exists, f double prime of C exists, f triple prime, so on and so forth. All of them exist. We define T of f c x to be just the infinite series summation I equals 0 to infinity fi, the ith derivative at C, by I factorial into x minus c the whole power I. Okay, now notice, even though I have used functional notation, okay, this is not necessarily a well-defined function of x. This is not necessarily a well-defined function of x. Okay, it can happen that this series does not converge. It's very possible that that series does not converge at all. So one interesting question is, when does T f c x converge to f of x? When does this happen? And in the next module, you will be in for a shocking surprise. This is a course on real analysis, and you have just watched the module on a notation for Taylor polynomials.